Okay, I will start. So welcome everybody to the Asia Pacific Analysis and PDE seminar. It's really a great pleasure today to welcome you all, and in particular our host speaker, Goro Akagi from Tohoku University. I got to know Goro, as I already mentioned before, as a PhD student first, and I read a lot of papers from him on probably on his main contribution to evolution equations governed by the difference of two subdifferential operators, where he studied a lot of regularity properties and asymptotic behaviors. And then later I had the chance to meet Goro in South Korea at a major conference on variational mathematics. And since then, we lost track a little bit, but Goro went to Munich and I went to Australia, basically. So we could not meet, actually. And Goro will speak today about traveling wave dynamics for one-dimensional constraint Allen-Cahn equation. So it's a great pleasure, and please start.
Okay, thank you very much for your kind introduction. And first of all, I'd like to thank Daniel for his kind invitation to Asia Pacific Analysis and PD seminars, and also I'd like to thank all the organizers of this seminar for giving me this opportunity. Okay, so today I would like to talk about some joint work with Christian Kuhn from Munich and Kenichi Nakamura from Kanazawa University. And so it is concerned with traveling wave dynamics for Allen-Cahn type equation, but the equation has some constraint conditions. So it looks now not in divergent form, but fully nonlinear one. Okay, so let me start. So first of all, I'd like to explain what does the non-decreasing constraint means. Okay, so in this talk, the non-decreasing constraints on evolution mean that the solution is non-decreasing in time variable at each point x. Okay, so namely, it is equivalent to the non-negativity of the time derivative of u. So such a constraint problem appears in the study of reversible phase field models, so which appears in the study of mainly reversible phase transition phenomena, say some kind of a special alloys or some irreversible solidification of vegetable gelatin and so on. And also such kind of phase field model appears in the study of brittle fractures, so damage mechanics. Okay. So here, let me explain how such a non-decreasing constraint appears in the irreversible phase field model with the brittle fracture model. So let U denote the displacement field of material. So in a sense, now we are thinking about material and make a deformation. Okay. So then U denotes the displacement field of the materials. Okay. And Z denotes a phase field variable, which intuitively mean that Z is equal to 1 if the material is cracked at point X and T. Okay. But the Z is still equal to 0 if the material is not cracked at X and T. So in a sense, Z describes the degree of damage, very roughly speaking. So therefore, Z of xt is supposed to be non-decreasing in time because of the irreversible, the nature of damaging phenomenon, okay? Unlike the displacement field, because the displacement field is completely reversible variables in time. And in the damage mechanics, the fracture mechanics, the following system of equation is introduced and vigorously studied. The first one is equation for the displacement field. And the second one is the evolution for the damage, the phase parameter. And here, okay, so the first equation is simply given as a Euler-Lagrange equation of certain free energy functionals. Okay. The second equation is look like a gradient flow. Okay, so actually the inside of this blade correspond to the negative minus pressure derivative of certain free energy functions. So maybe it should be F. But we add positive part function in the right-hand side because so then the time derivative is always non-negative. So in a sense, it is a modification of gradient flow in order to realize irreversibility. And here the F epsilon is given like this. Okay, so this part corresponds to the modic molecular energy. Okay, and this part corresponds to the elastic energy. Okay, so this kind of system have been studied. Okay, so maybe the first introduced by Fleming and Neger at the end of the last century. And it has been studied by many people, say Elena Bonetti, Julius Kimperner, and so on, many people. And also the late independent version of this problem has been studied by Alessandro Mielke and Thomas Lubitschek, and also many other people, the Rossini and Carlo Rossi and Chiara Danini and so on. And also from more numerical point of view, the parabolic version has been studied, the double parabolic version has been studied. This model is introduced by Takaishi and Kimura in 2009. And yeah, so they introduced this model for implementation of numerical schemes. Okay, and so recently I also work on this original the Fleming model with Julius Kimperner, and we proved local in-time existence of solutions without any regularization. Okay, but today, okay, so let me now focus on more structural properties of these kind of things, problems. Now, actually, the equation for the phase parameter has this kind of structure, so which looks like a gradient flow, as I mentioned, but now we add some modification that is a positive part function. Okay? So in order to realize a non-negativity of time derivative. And this problem can be rewritten like this. So actually, by applying the inverse function of positive part function to both sides, so then this problem appears. So this, okay, so here that some function nu appears. So that it looks like maybe very roughly speaking, it plays a role of Lagrange multiplier. Okay, so and actually the Lagrange multiplier modifies the direction of gradient in order to realize a constraint condition, right? So actually this law modifies the minus gradient of J evaluated at U of t in order to realize time derivative of U is always greater than or equal to 0. And this nu can be characterized by an element of indicator function supported over time non-negative half-line acting on time derivative of U. And actually the domain of this subdifferential operator is this negative half-line. So therefore the time derivative is always non-negative. And by the way, by comparing these two equations, one can find that mu is nothing but the negative part of the minus gradient of J. And another advantage of this reformulation is that the original equation is fully nonlinear equation. It is not in divergence form. But this reformulated form will be in divergence form. So I will show you the more explicit example. But anyway, so corresponding equation to this form will be in divergence form. Okay. So therefore, so that it's much easier to apply energy method to this form than the original one. Okay, so now let me remark that so this equation has some so how to say so in this equation we observe some conflict between stabilization and constraint. Now actually in the gradient flow equation, solution evolves in such a way as to decrease its energy because it is a gradient flow, so solution evolves in the steepest descent directions in order to decrease its energy. But on the other hand, sometimes such a evolution may violate constraint condition. So in such a case, constraint condition prevents stabilization of solution. So in this, in such a constraint gradient flow equation, we find some conflict or struggle between two different effects. And as a result, the set of equilibria may be bigger or richer, and the dynamics of solution will be more complicated. Okay. So therefore, the aim of this research is to investigate what kind of effect or what kind of influence occurs to large time behavioral solutions in such a dynamics of gradient flow with non-decreasing constraints. Okay. But of course, it's more difficult to handle the full system of the brittle fraction model and so on. So therefore, in this talk, let me restrict ourselves to simpler PDEs, but with non-decreasing constraint and also gradient flow structures. So that is one-dimensional Allen-Cahn equation with non-decreasing constraints. So namely, that we will discuss the large time behavioral solution for this one-dimensional equation. So W is a W-well potential. Okay. So maybe the most fundamental case is the derivative of W potential is U cubic minus U, something like that. Okay, so by the way, this equation was also studied in my different joint work with Mesut Efendiv, published in 2019. And in this paper, we handled the Cauchy-Dirichlet problem in bounded domain in Rn. Okay? And we proved the well-poledness and smoothing effect and energy dissipation and so on. But one of interesting property is that due to the conflict between stabilization and constraint, the smoothing effect cannot be realized in a classical way. So in a sense, the smoothing effect and the energy dissipation, which are particular phenomena for parabolic equation, occurs only in some restricted region of domain and so on. So therefore, that we cannot always get smooth parabolic smoothness all over the domain. But in a sense, we can extract such kind of parabolic properties by introducing some specific subset in a functional space. And another important finding in this paper is different reformulation of our problem. So as I mentioned, we can introduce reformulation of this fully nonlinear equation to divergence, the different equation in divergence form. But this is another one. And it is in terms of an obstacle problem, okay, for semi-linear equation. But the obstacle function coincides with initial data. Okay, so this reformulation also plays a crucial role in my today's talk. So I will explain a little bit more later. Okay, so before going into the details, so let me briefly recall the Allen-Cahn equation, the standard classical Allen-Cahn equation and its traveling wave dynamics. So now let us consider such kind of traveling wave Allen-Cahn equation without positive power function. And F satisfies such properties, but okay, so this, of course, you can imagine F is equal to U cubic minus U, and it satisfies following. It has such a graph with 3 different zeros, okay? And the 2 zeros, the A minus and A plus, correspond to the stable equilibrium, okay, constant equilibrium, and A0 is unstable equilibrium. Okay, and F also has primitive function, which has a WL structure like this. And the two minimizers correspond to the stable equilibrium, and one local maximizer corresponds to the unstable minimizer. And such Allen-Cahn equation describes the phase separation phenomena in the various contexts. And also it is well known that Allen-Cahn equation is a L2 gradient flow or such Ginzburg-Landau type free energy. So namely, the right-hand side can be written as a minus pressure derivative of U. So, okay, so as I go like this. And therefore, the J of U is non-increasing in time. So J is Lyapunov function for this problem. And the traveling wave solution is one of typical feature of Allen-Cahn equation, and also the reaction diffusion, more general reaction diffusion equation. Okay, so the traveling wave solution is a solution given in this form. Okay, so namely the phi of x minus ct. So the phi is something like this, this graph. So this graph. And the profile of graph is same, but it translates in space, in time. And so namely that in order to investigate such a traveling wave solution, we simply substitute this relation to the equation, Allen-Cahn equation. So then the following profile equation follows. And also we also impose asymptotic condition for phi. So namely this phi connecting two stable equilibrium at infinity. So namely, so this solution this traveling wave solution is describing the transitional phenomena of between two different stable equilibrium. Okay, and then the C denotes the velocity of this traveling wave, and it is determined by the difference of energy at two equilibrium. For instance, if the WL potential takes a minimizer at A minus and A plus, the value of W at A plus is a little bit larger than that of A minus. So then A minus is much more stable. So there is some incentive of phase transition from A plus to A minus. Okay? So therefore, in such a case, the C is greater than 0, C is positive, and this traveling wave moves in this direction. So namely, at each point, the state transits from A plus to A minus. So this is a traveling wave solution. And such a phenomena have been studied by many authors, but so here let me only recall only 2 papers. The first one is Fife and McLeod. So they studied the existence and uniqueness of traveling wave solutions by using a phase plane analysis to investigate such a ODE or profile equation. And also they proved exponential stability of traveling waves. Okay. So they imposed some assumption on initial data. So very roughly speaking, this is telling that initial data has some limit at plus infinity greater than unstable equilibrium and a little bit less than unstable equilibrium at negative infinity. So then the solution corresponding to this initial data getting close to traveling wave solution. And the more important thing is that such a convergence or stabilization occurs at with some exponential rate. So in this paper, so they used the classical Schauder estimate and dynamical system Selly and Savant super solution method. And in 1992, the Shifu Chen developed this method, and he succeeded to prove the similar results by using only Savant super solution method only. And as a result, he could cover the he can cover the non-local reaction diffusion equation as well. So now let us move on to our target issue. So that is a constraint Allen-Cahn equation. So difference is only this positive part function, and we will denote this problem by AC plus. And the assumption for F is completely same as before. Okay. And the positive part function is defined in the standard way. Okay, so now let us recall the structure again. So this equation has some gradient flow-like structure, but we have a non-decreasing constraint. On the other hand, this equation still shares the same Lyapunov function with classical Allen-Cahn equation. So namely, this time derivative is non-decreasing in time. Okay, we can see this property easily by using this reformulation, which I explained before. Okay. So now this equation, okay, so this part corresponds to the second derivative of u plus minus f of u. Okay. And we still have some additional term which plays a role of Lagrange multiplier. Okay. But if we test this equation by u sub t, this part corresponds completely same as the classical Allen-Cahn equation. But we still have this additional term. But fortunately, the product between mu and u sub t is always equal to 0, because the mu is a section of this subdifferential evaluated at u of t. So therefore, this is non-zero only when u sub t is equal to 0. So namely that this equation always holds true. So only this test makes no difference from classical Allen-Cahn equation. Of course, if we test a different thing, say u or Laplacian of u and so on, so there arises some additional term, additional effect arising from this nu, and this operator is unbounded operator, so it may make some trouble, but by testing u sub t, we have no problem at all. And another reformulation which I announced at the beginning of this talk is this one. Okay, so this problem can be related equivalently to this obstacle problem. So obstacle problem means that the both of them are non-negative. Okay. But either this one or this one should be equal to 0 everywhere. Okay, so and usually this one is called obstacle function, and usually it is different from initial data. But in this reformulation, obstacle function coincides with initial data. Okay, so this is a characteristic point of this equation. And actually, this kind of obstacle problem are also studied in context of pricing problem of American option, but I think it's not so well studied. But anyway, so in order to reformulate this problem, we have such a peculiar obstacle problem. And then this same nu is characterized by this. Okay, so different operator. So in the former one, this subdifferential operator acting on U sub t. So in a sense, this is a higher order nonlinearity. But on the other hand, the constraint set is constant set, so it's easier. But in the latter one, this nonlinear operator acting on U itself, so in a sense, lower order nonlinearity. But constraint set may depend on X. So the handling of such a nonlinear operator is a little bit more difficult than this one. But anyway, so in a sense, we have advantage and disadvantage in each formulation. Okay, so in this talk, we should discuss existence and uniqueness of traveling wave solutions first, okay? And then we will discuss stability. So especially, we want to discuss exponential convergence of general solution to traveling wave solution. In fact follows, in order to fix idea, we may restrict ourselves to balanced potential. So balanced potential has two double well like this, the same minimum value, okay, global minimum value. For this potential, classical traveling wave solution for classical Allen-Cahn equation has zero velocity because two bottom takes the same minimum value. So there is no no driving force to make a transition. Okay, but in constraint Allen-Cahn equation case, the situation may change, even if the potential has double wave structure. Okay, so now let us go back to this balanced double wave potential. Okay. So if we simply substitute this relation to the constraint Allen-Cahn equation, so then the proper equation reads like this. Okay, so maybe one can handle directly this ordinary differential equation with some non-smooth nonlinearity. But okay, so it's not so easy. So we would like to introduce an alternative profile equation to construct a traveling wave solution. The idea is as follows. Okay, so let us consider alpha between -1 and 0. So this is a new constant equilibrium for our positive part function version of Allen-Cahn equation, because this equation has this form. Okay, and now if we substitute alpha here, so this is negative, and also alpha, if we take such a constant function, this is equal to 0. So therefore, the constant function with value alpha is another steady state. So for constraint Allen-Cahn equation, which was not equilibrium for the classical Allen-Cahn equation. And then now let us consider the traveling wave solution connecting this new equilibria and a plus, or so stable, most stable equilibrium. But we have non-decreasing constraint now, right? So time derivative is always non-negative. So therefore, if we consider the initial data at time minus infinity is identically equal to alpha, so then the solution u of xt is always greater than or equal to alpha everywhere. So therefore, it means the region of the graph in the rest of region is prohibited, okay? Because you never go below alpha. So therefore, okay, so let me show you some graph. So this is the original graph of potential, but now the solution of u is confined here only confined here in this region. So therefore, the graph might be replaced by such a cutoff graph. And actually, such a cutoff comes from the reformulation in terms of the obstacle problem. Because now we regard this condition as an initial condition at time minus infinity. So then the initial data you note is replaced by alpha. So therefore, this is a reformulated equation corresponding to this initial condition. And now the sum of these two terms can be regarded as a derivative of W and this indicator function. Okay, so it's not really, it may not be correct, rigorously speaking, because this is non-smooth functionals. But anyway, intuitively speaking, we can regard the sum of these two terms can be regarded as the derivative of W plus indicator function. And then the graph of sum of two functions looks like this, because the indicator function supported over alpha plus infinity is something like this. And now adding it to the double wave potential, we have this graph. So now we find that originally two equilibria have same minimum values. But in this cutoff functionals, this minimum value is apparently greater than the global minimum. So now there arises some incentive for the solution to transit from alpha to A plus. Okay. So therefore, we can expect the existence of moving traveling wave solution for constraint Allen-Cahn equation, even for the balance of potentials. Okay, so now let us substitute this relation to the reformulated equation in terms of the obstacle problem. So then this profile equation is derived along with the asymptotic condition, which is connecting profile function at alpha and 1. 1 is a global minimum. Okay, so now it looks a little bit easier to solve, and actually we can prove the existence of solution phi, especially monotone function phi, and so on. And as we expected, we can prove the velocity of traveling wave is negative when alpha is different from -1. Okay, so our result. So before showing the main statement, the statement of cell, let me show you the picture of our traveling wave solution. So our different from the classical Allen-Cahn equation, our new traveling wave solution has a degenerate profile function. Actually, this profile function is strictly monotone here, but then it is constant in the rest of the negative half-life. And there arises some free boundary point, and it moves velocity C alpha. Okay, so let me show you the more precise statement. So for each alpha between -1 and 0, and our problem has a traveling wave solution of this form with profile function phi alpha and C alpha, and connecting 1 and alpha. Okay, so this alpha from this alpha. And the profile equation is provided in this form, and which is also equivalently rewritten like this as an obstacle problem. And the phi alpha has W to infinity regularity, but it loses classical regularity at the free boundary point. And alpha is between alpha and phi alpha is between alpha and 1, and the derivative is non-negative. And the velocity is negative in this setting. Okay. And another point is that there arises some free boundary point such that profile function is constant in the negative half of the region, and it is strictly greater than alpha in the positive half of the line. And in this positive half of line, real line, the phi alpha solves the classical Allen-Cahn equation. Okay. So therefore, second derivative has discontinuity at the free boundary point. So therefore, the C2 regularity never holds true. And okay, so in fact follows, we normalize our profile function such that this free boundary point is the origin. Okay, so this is the picture again. So in the rest of time, okay, so before going to the stability part, so let me mention about a couple of features on the traveling wave solutions. The first of all, for each alpha, the velocity constant and the profile function are uniquely determined. Of course, the profile functions are unique up to translation. But on the other hand, in contrast with the classical Allen-Cahn equation, we have one parameter family of traveling waves. Okay? So in the classical Allen-Cahn equation case, the traveling wave solution is unique, completely unique. Okay, but now we have a one parameter family depending on alpha. Okay, so now let us move on to the traveling wave, stability of traveling waves. So here we would like to consider the exponential convergence of general solution for the constraint Allen-Cahn equation to traveling waves, as in the classical Allen-Cahn equation. But we cannot expect stability of traveling wave solutions in the classical sense, because we can prove that its instability. So actually, we can easily explain this one, because, okay, so let us consider some. Okay, so this is phi alpha. So phi alpha x minus c alpha t. So this is this is a traveling wave. And now let us consider very similar traveling wave, but with different alpha. So that is alpha prime and alpha prime x minus c alpha prime t. Okay, and we can prove that if alpha is have some order, so then the traveling wave, the velocity of traveling wave is different. So something like this. They both of them are negative, but the velocity of the red traveling wave is slower. So it means that even if at the initial moment, two traveling waves looks very similar, but as time passed, the traveling wave is getting apart. So therefore, the stability cannot hold true in narrow infinity topology. So therefore, that we have to restrict the basing of the class of initial data to prove the exponential stability of solutions. So in our result, we will introduce the following assumptions. Okay, so alpha is now between a minus and, okay, so a minus corresponds to -1 and a0 is 0. Okay, and we impose some regularity assumptions, and okay, so lim inf of u0 is greater than a0. So this means if, okay, so like this. So the limit of initial data is a bit greater than this unstable equilibrium. So this assumption is totally same as in the classical Allen-Cahn equation case. And also we assume initial data is between a minus and a plus. Okay. So this part is same as in the classical Allen-Cahn equation, but here we assume the supremum is strictly smaller than A plus. Okay, so I see. Okay, so this is somehow the technical assumption. We could be relax it. Yeah. I'm not so sure whether we can completely remove this assumption or not. But anyway, so if we assume this one, we can do it. And also we assume this assumption. So this means that the initial data is constant at some point in the negative half-line. So this is used to define the free boundary point for the solution of our problem. And actually, as I told you, this equation has some feature like obstacle problem, and maybe that it is worth to investigate the motion of free boundary point and so on. So therefore, in order to consider the free boundary point, we assume this one. So then our results follow that follows. So if alpha is between like this, and we also input some additional assumption, if prime alpha is positive. So okay, so this is still technical assumption, and so this is telling that. So as I told you, we cut off potential function. And now this is alpha and this is A plus. And this assumption is telling that this minimizer of such a non-smooth WA potential is still stable equilibrium. So in a sense, of course, we can cut anywhere, okay? And but if we cut WA potential in a different way, the cut-off WA potential looks similar to monostable case or something like this, in a sense. But this assumption guarantees that the even cut-off potential is bistable setting. So actually, in order to construct some comparison functions, we actually need this assumption. But anyway, so let us assume this one in addition to A sub alpha. So then all the solution U of constraint Allen-Cahn equation for initial data U0 converges to profile function, traveling wave solution with some exponential rate. Okay. So this result seems the same as in the classical Allen-Cahn equation case. Of course, that we restrict the class of initial data. Okay, but now we have free boundary point. Okay, so free boundary point means solution looks like this. So this is the initial data, but even each solution has similar structures. So, okay, so the solution cannot decrease, so like this. So then there arises some free boundary point. So this is R of T. Okay. So therefore, we can also prove the exponential convergence of free boundary point to that of traveling wave solution, and its rate can be estimated from above by exponential rate with half constant. Okay, so finally, let me explain briefly the idea of the proof for the phase plane, the exponential convergence of to the traveling wave solution. So first of all, I may want to know that the standard comparison principle, comparison argument does not work for classical our constraint Allen-Cahn equation, because a super solution for the constraint Allen-Cahn equation cannot decrease. But usually, when we apply the sub and super solution method, we want to confine. We want to control the behavior of solution from above and below by using the sub and super solution. So in order to do that, the super solution should decrease in order to restrict the region of graph of solutions. But in this non-decreasing feature, we cannot apply such a method. So therefore, our proof consists of four phases. So in each phase, we have to wait worldwide, finite time, in order to realize some specific situation. Okay. So here the phase means such kind of things. Okay. So in each phase, we have to wait worldwide. We cannot no idea how long is it, but it is still finite. Okay. Then some situation occurs, and then we will enter the next phase, and then we also wait worldwide and so on. So in the first and the second phase, so finally, the following situation occurs. After a certain time, the coincidence set of U with initial data is rewritten like this. So it is very important because then the obstacle function can be replaced by constant function. So now it is more tractable, and we can, for such reduced problem, we can apply the sub and super solution method. Okay. And the third step, we will prove quasi-convergence of the orbit. So namely, the shifted solution converges to the traveling wave along some subsequence. So here we will use the energy method. And finally, we will start from a situation that initial data is closely sandwiched by sub and super solution. So that is made of this traveling wave solution with some error. And then we will prove the exponential convergence by using the sub and super solution method. Okay. And finally, so here let me give a remark on method of proof. Now, actually, Xinfu chain. Okay, so this strategy is the third and fourth phase look similar to the work of 500 Mach load. And Xinfu chain developed a strategy of the 500 Mach load to reduce methods, and he succeeded to prove everything only within the frame of sub and super solution method. And actually, we may try something similar thing, but there arises some problem because by using the strategy of a chain, okay, so the idea of a Xinfu chain is very very brilliant and very fantastic. And actually, at first, the solution is sandwiched by sub and super solution. But this sub and super solution includes vertical error. So in a sense, this solution go down and this solution go up. So the vertical error will decrease. Okay. But on the other hand, the horizontal error increase due to the construction of these comparison functions. So therefore,
Goro, sorry, I need to just say that you still have 3 minutes.
Okay, I will finish. Sorry. Yes. Yeah. And then, so he divided region to 3 pieces, and in the middle, he applied a strong maximum principle to improve the horizontal error. And the rest, he used the smallness of derivative in these region, in the graph of traveling wave profile in this region to control the horizontal error as well. But now our traveling wave solution has degeneracy here, and it may increase drastically. It may increase, right? So in this region, we can take a sufficiently large border, but here we have to precisely control the region, okay? So therefore, the argument is much more involved compared to the original work. Okay. So finally, let me give some remark which is related to the Stefan problem, maybe. And actually, in this study we also have a free boundary point, and so maybe that it is quite natural to consider what is the motion equation for our free boundary point. And for sufficiently regular solution, we could derive a motion equation. So that is given like this. Okay. And such a motion equation has been studied in the context of Stefan problem, and Ihondu is one founder of this study, and many people following. And I cannot insist all literatures. I just mentioned the part of the works. But anyway, so in the classical Allen-Cahn equation, the first derivative appears, but in our case, the third derivative appears, because in our problem, zeroth derivative and first derivative and second derivative of u are automatically determined due to the equation. So therefore, the freedom first appeared in the third derivative. So therefore, our free boundary equation looks like this. Yeah. But I haven't. Okay, so this is just a remark, and all proofs which I gave due to the four phases, and yeah, it is not used, but anyway, so maybe that it is also interesting viewpoint in the future. Okay, thank you very much for your kind attention. Okay.
Thank you so much, Goro. This is really very interesting. And again, you have two subdifferentials, and even not as a difference, but you have two subdifferentials in your evolution equation. Are there any questions or remarks? Please raise your hand, and then I will unmute you, or Ben will unmute you. No questions? Maybe Yihong or Wenhui, experts on Allen-Cahn equation. Okay, well, there is still a chance to ask Goro another question later in the coffee break. So you should all have received an email with a coffee break afterwards, and hopefully Goro will also join us. Yeah. Okay, then please join me, and thanks Goro again for this very nice talk. And yeah, so then Ben, I'm done actually. Ben? Ben is not here?
I'm here, yes.
Okay, good.
Yeah.
So I think, yeah, the seminar is done actually.
Okay, so let us meet at the coffee break. Yeah,
yes, okay.
Okay, see you.
See you later.
Thanks, Goro.
Thanks, Goro, for the nice talk. See you in the coffee break.
Thank you very much.
Okay, bye.
Yeah, later.